the current theoretical problems that we have in understanding what's going on in some of the systems. Some of them are problems we've had for a number of years and still have not got any further with. So I hope I'll pull out a number of examples. So my aim is to pull out maybe about 5 examples. So as we go on, you'll figure that my team is a lot of different people working together, split between physics, chemistry, materials, engineering. And it's all about how can we actually get light to interact with materials in new and interesting ways. And you'd have thought, since we understand everything about light from Maxwell's equations 150 years ago, there would be nothing here. And what I think I will try and convince you of is that there's still a huge amount here that we really don't understand, and it's quite surprising. So there are lots of collaborations, a lot of them in Cambridge, and Oren will talk a bit later about another aspect of these materials. So we do interact with theorists, but we completely destroy them as much as we can. So there's lots of opportunities here. So I'm going to talk about a set of different examples. I'll talk initially about how we make things. So often when you're trying to make things on the small scale, which we'll see is very key for actually getting new sort of phenomena from light-matter interactions, one of the things is how do we actually make this on realistic size scales? And that produces problems of how do you assemble things. So I'll talk a little bit about that. I'll talk about systems which are disordered, which turn out to be harder to describe than things which are ordered. I'll try and come to this topic where we try and understand what does an interface for light look like down to the atomic scale. How might we describe that? Because that's not what's in Maxwell's equations. And then I'll go further on to this boundary between quantum mechanics and classical electrodynamics and how we make that work. I'll talk a little bit about forces, and then I'll see how far I get. So I wanted to start in this area here, which is on how we actually can think about making things. So this is actually something that has now been commercialized. It's been produced on the large scale. So this system here is actually an opal, like you dig out of a mine in Australia. And opals are made of lots and lots of little glass spheres which are stacked perfectly like oranges. And one of the things that we've known about them for 30, 40 years, but one of the things is that we've not had a way of making them on the large scale. So they're made naturally over millions of years, just in salt-laden water which sediments out and it grows as little spheres, and they somehow, the lowest state turns out to be stacked. But actually in the lab there's no process that we found to make these. So we actually devised a technique where, so the main problem is that you have spheres and they're in some sort of solvent, and you want to get rid of the solvent so they stack perfectly. But as you're making everything denser, you're removing the solvent, at some point the system has a phase transition and all the spheres stick together and all the solvent goes out. And so there's a kinetic trap of the system. It stays in this disordered state and it's very hard to anneal it. So essentially the trick that we used here is that we take these spheres that are actually made out of plastic, polystyrene, and they're coated with a material which is like chewing gum. It's soft when you heat it and you push it. And that acts as the solvent. So we don't put any other solvent in the system. So these are, if you like, sort of chewing gum coated cannonballs. They're very small because it's only when you make them small enough on the scale of the wavelength of light that you start to get these really interesting color effects. So only when I stack them and they're a particular size will I say get a green out of the system. So we make films of this, and then what we find is that when we actually shear this film, so the solvent is entirely just this shell here, we shear them against each other, they order perfectly. So, you can look at different aspects of why that happens in the X-ray, but basically the shearing, what happens is the spheres actually it's completely kinetically trapped, so the thing it's like chewing gum, right? So you have to put forces onto it, but then the system wants to slide. So it starts to self-organize into these planes that will slide past each other. That's how the shear slips. So the shear stress is yielded. So the system wants to organize into these sheets, and then the spheres want to have, the lines of spheres want to sit in the dips of the other spheres. So they want to line up in these lines of spheres where that line sits in that groove. So that's why in each layer it starts to now be hexagonally close packed. And what happens is any sphere that's out of alignment, all the forces start focusing on that sphere to push it back to some alignment. So you end up shearing backwards and forwards just a few times, and you start to get really, really good packing. There is no model for this. So almost all of the self-assembly going on in soft matter systems is in some sort of solution phase. This is highly non-equilibrium. So there's huge sort of rotational forces and extensional forces that are going on in these interactions here. And yeah, I can write down a very simple sort of model that will give me something that looks about right, but it's not even a toy model. So it just shows you how little we understand about some of these systems. Just to show you we can make huge amounts out of it. So this material, just depending on the sphere size, gives different colors. People in the fashion industry are interested. We now have backpacks. People are trying to make building coatings out of it. You can do all sorts of functional things because the color comes just from the structure. So these materials are just transparent spheres. There's nothing complicated about them. It's just how you stack them. So this is a very nice material. Except it's probably the most boring material you can imagine. It's a lot of spheres that are stacked regularly. What we really want to do when we're changing the interaction of light and matter is do much more complicated things. So I can start to ask questions, what happens if I make my spheres ellipsoidal? What will happen to the shear ordering? Or I make them into some sort of pyramidal shapes? What could I do to make more interesting, complicated structures? What happens if I make spheres of different sizes and I shear them? Can I get superstructure ordering? And, well, so we just have to do it experimentally because nobody can tell us. So that's one sort of challenge that exists in this space. The reason, so this is a sort of volume effect. Essentially, the light will penetrate many layers into the structure. So maybe 1,000 layers of these different spheres, and this complicated interference is what gives the color here. So that's nice, but if I wanted to change the color dynamically, say, then I have to change the entire volume. And that's quite a large volume. So if I want to make a low energy switching material, which we'll talk about later, then I'd really like something which effectively localizes the light more and affects it. And for that, we're actually going to use a different effect, which is called plasmonics, which just means that we use metallic systems, not plastics and glass. So metallic systems have all these free electrons in them. And there are some metals particularly, which are very good for this. So gold or silver or aluminium or copper. And basically the electrons respond to incident light by sort of shaking at the same speed as the optical field, so 10 to the 15 times a second. And the electrons are sort of oscillating backwards and forwards. So if you look at Maxwell's equations and you just solve what goes on here, you find that there's a particular frequency or a particular color of light that will actually maximally shake those electrons, because those electrons create their own near field. There's a dipole created and there's a shape resonance in the system. And that's actually how stained glass is made. So stained glass uses particular nanoparticles of particular shapes, and they have a particular color which is dependent on the shape of the nanoparticles inside the glass. But this is not known about for 20, 30 years, and what we're interested in is actually concentrating the optical field. And here you can see the field lines from the oscillating electrons. They are more concentrated at the two poles here, but they're not that concentrated. What happens that's interesting is when I bring another particle close by, then this near field, as well as the light that I'm shining onto the system, will affect the electrons in this particle. And they'll oscillate in a way that then affects the electrons in this particle. So there's a very strong interaction in the system. And it's a bit like a dipole-dipole interaction. It's a classical interaction, like two bar magnets, which you can feel when you bring them very close together, have a strong interaction. So this is fearsomely distance dependent. So we became more and more interested in actually controlling these gaps on the scale of a nanometer. So what happens is there's a particular color that gets trapped in that gap, and the closer you make the smaller the gap, the redder that is. And it's like a capacitor. The energy of the system drops, becomes a redder system as you confine it more tightly. So we've done a lot of different things there. Well, I think we'll come back to all of that. So one of the things that I want to show you that's confusing us at the moment is a system that we're trying to make that's dynamic. You know, what I'd like to be able to do is to say change the gap size here, which would change the color of the resonance. So I could make materials which changed color. So this is one attempt that we had to do this. This is a gold nanoparticle, and again it's a bit similar to before. I've put a polymer coating around it. And this polymer can expand and contract and actually put sufficient forces on to be able to move these gold particles further and closer away. So now these gold nanoparticles are actually much, much smaller than the wavelength of light. So here's a film of that particular material. It has maybe 20-30% fill fraction of gold inside it, and the rest of it is this polymer which is solvated with water. And you can see the wavelength of light is bigger than the screen here, bigger than that image. So I have some sort of effective material here. It's what we would call a metamaterial. So I should be able to get some average property of this system. So one interesting thing that I can do is I can just look at the color of the system, and already I have a problem in trying to go between gold, which has a reflection spectrum that looks something like this, and the polymer we're using, which has a very flat reflection spectrum like that. And if I try and make some sort of model about what the reflection spectrum looks like, I start to get into problems because of these very strong couplings, because these particles are very close to each other. So a mean field model doesn't really work in this system. But because it's disordered, I can't use all the typical formulation that we have for, say, periodic materials. So I'm faced with doing extremely difficult simulations that have millions and millions of these spheres in, and they're interacting very strongly to each other. So yeah, maybe the other thing I should say, so we can do this sort of thing reversibly. This is actually the individual particles in little droplets. These are about 50 microns across, and they're red, just like stained glass can be red, because they're scattering out the green light here. And if I heat them slightly, what happens is all of those condense together, and actually I get this effect where the centers are now black and the rest of it is transmitting light. It's a bit like, it's a biomimetic analog of things like squid or octopus, and that's how they change their color. They take dye-based color and they quench it all together, or they make it go further apart. That's how they try and do that. So that's what we're trying to do here. And so this can work very fast. We can also use this system, I mean, actually the water gets sucked in if we cool it slightly, a few degrees, and if we heat it a few degrees, the water gets pushed out, and we can sort of analyze what's going on here to understand what the effective parameters of this material are. So for instance, the permittivity, essentially the refractive index squared, well, it actually, in this spectral region here, goes from being something that looks like a dielectric, say a glass, a colored glass, to something which is metallic. And you can just switch directly backwards and forwards between these two states. So everything changes when you switch between those states. And again, we really don't have any way of predicting what it is we're going to get in this system, because the coupling is very strong. So what we're now doing is we're essentially making these into sort of mirrors. So they reflect light, they're gold. They reflect light, but wherever the light beam arrives and it slightly heats the mirror collapses and changes its shape. So I have a mirror which is deformable by the very light that's being reflected from the mirror. So very strange sort of nonlinear systems that are rather useful in say, in astronomy, by taking out the twinkle of the atmosphere. You're trying to correct from atmospheric distortions, or very equivalent things in lab-based technologies for light. So we would like to have something like this, which just on demand changes, and we can control the reflection of the light with the light beams themselves. So okay, so that's a typical problem. Then we have a system, so that's very complicated, so let's go to a very simple sort of version of that system. Let's just take two gold nanoparticles. So these are about 100 nanometers across, so they're much, much bigger than the size of atoms. But I want to put them as close as possible together. So you end up having to try and make something like that, say with a layer of graphene in between, because that's only one atom thick. So when I do that, then the electrons that are excited by light will be interacting very, very strongly between these. It's actually a bit difficult to make. It doesn't want to form that way. But I can use a very simple electrostatic analogy. If I take this particle and I put it onto a ground plane, then essentially all the charges here have image charges below. So any dipole here has an image dipole. So in fact, this system behaves identically to the single dimer. So we've used this a lot in our labs. So what we're doing here is, so for instance, we take a gold mirror, we'll put a very thin sheet of material upon it, and we'll put a gold nanoparticle on top. And the light gets trapped into this very tiny gap, but only a particular color of light. So in this particular case, it's a yellow color that sits underneath here. And the way it works really is that I can think about underneath here, I have a metal and then dielectric and a metal sort of waveguide. So here the electrons can move, and this is sort of a passive material in the middle. And it turns out I can calculate what light does in something like that. And you would imagine that if I bring two metal surfaces together and they get much smaller than the wavelength of light, the light would be squeezed out. But it turns out electromagnetism is not like that. There's one extra mode of the system that doesn't do that, that really likes to be in the gap. And in fact, as you squeeze it together, the light sits very nicely in the gap and decays off extremely rapidly into the metal. So it's really just, it's a bit like a coax cable, which is shrunk down very small. And coax cables can happily take radio waves, even though the coax cable is much smaller than the radio wave. So it's the same mode that we're using here, shrunk down by a factor of 1,000,000 or so. So we can calculate the modes that exist in there. They go very slowly, actually. Then the only other thing we realize is that actually there's a facet on the bottom of this particle and these edges here which reflect these modes. So I get some sort of standing wave states that sit in there, but this can be 10 nanometers long. So I can confine light into something maybe 10 nanometers long that way and less than a nanometer that way. And some years ago we didn't believe things like this were possible, and now these are completely routine. The mode looks something like that. So I have a very strong and intense mode for light that actually I can couple to. So this nanoparticle on the top acts a bit like an antenna. There's another mode in the system which is more distributed. And so free space light can couple to this mode here, which couples to this mode here, so it puts light very efficiently into that gap. So that's, otherwise we couldn't really see what was going on in this system. So we've been using these modes for a bit of time. We actually understand quite a lot about this mode description from classical electromagnetism. So it is difficult, however, to do the simulations because I have to worry about discretizing space when I'm doing these sort of simulations for these modes. You know, that gap might be 0.9 nanometers. So then I have to discretize space on a 0.1 nanometer scale, which is less than the size of atoms. And so now we start to worry about, is this valid for electromagnetism? Am I in the right limits here? So then we start to worry, well, actually, of course, my gold is made of atoms. So this is a simulation that I might do electromagnetically, and this is just a vague picture. So where is the edge of my gold atoms in this simulation? I told you this is 0.9 nanometers, and that's because when I solve my electromagnetics model, I get a fit to the data, which is very, very clean, when I make the gap 0.9 nanometers. That does not mean the gap is 0.9 nanometers. What would I mean here? Does the light see this corrugation? Gold atoms are about 0.3 nanometers apart. How should I treat that corrugation? What's the effect of disorder here? And I have one atom out of place. Should I see it? Was light trapped there more or not? What happens if I have a different crystal lattice plane here? How do I define what the dielectric constant is, the refractive index of a single molecule? Does that have a meaning? Is it just the polarizability of the molecule? Or do I have to do something else? So these are some of the problems that we're facing. It gets even worse because as I bring these closer and closer together, what should happen is this mode should head off into the red forever. And of course that doesn't happen. The reason it doesn't happen is because when it's close enough, actually electrons can quantum mechanically tunnel through the gap. And when they quantum mechanically tunnel, they basically discharge this capacitor which is existing from these two interfaces. So that's a quantum mechanical effect that I can see at room temperature in ambient conditions as long as we can look at the gap. And we did that a few years ago. So we actually had two tips. We bring them close together. We measure when the quantum mechanical tunneling happens. We look at the colors here. And about this point here, when the gap is about 0.4 nanometers, we start to see this quantum mechanical tunneling effect here. So basically it tells us we can only confine light a certain amount because quantum mechanics will actually take over and actually discharge the very large optical fields we're creating there. So already there's a problem here from quantum mechanics because we cannot solve this problem exactly. What we have to do is a fudge where we essentially do the quantum mechanics to understand what the, say, conductance of this gap is, and then make a fictitious material which has that conductance, and then solve the classical electromagnetism problem. So we're not really allowed to do that. and we can tell a nice fairy story that says it works, but it's a fairy story. And we've got well into this domain now, so this is a recent student in the group who's been making a molecule here which just nicely sits in these gaps, and this molecule is 0.4 nanometers. So it's at that quantum mechanical tunneling distance there. Again, we can measure, we're basically measuring the color of it here. It scatters light. It's a very simple measurement. You could actually look down a microscope and see this. It's not a subtle effect. We can see the color here, and we can change this atom in the middle here. When we change the atom, we slightly change the size. That's it. And we look at the color changing, and it fits no theory in any fixed up way. So we're sort of completely beyond what people are capable of doing. And the problem is that we cannot solve both, you know, the quantum mechanics of electrons in this system and in the gold system simultaneously, so that we can do both classical and quantum together. We should be able to just do the full quantum. If I'm doing a standard DFT calculation and an advanced one where I'm trying to include with this molecule gold atoms, I get to a nugget that's about 1 nanometer. And my 1 nanometer of gold is not sufficient to understand the electromagnetism that's going on here. So you have to always have a boundary between the quantum bit of the problem and the classical bit of the problem, and nobody knows where to put that boundary or how to make it work. So these are problems. Now let me show you an even more interesting problem that we have. So what I can do is I can put some molecules into the gap. I've just shown one of them here, but it's not true. There's a stack of these molecules, and they're all identical. They're very simple molecules. They've got one site on the bottom that anchors them into the gold. This is a sulfur atom here, 2 benzene rings, and then on the top here is a carbon-nitrogen triple bond. And the reason that's interesting is because we can scatter a photon off that, and we have some possibility of exciting that bond. And when we do that, it starts it vibrating, but the light comes out with a slightly different color. And I can measure that color. So it's measured in a very peculiar chemist's unit, but doesn't really matter. So this line here essentially corresponds to the vibration of this bond here, that carbon-nitrogen triple bond. So what this is here, this is a set of spectra, this black spectrum here, say, and I can look at it as a function of time, but that spectrum tells me all the bonds, the vibrational energies in that molecule. And we can do DFT calculations, the black curve here, and it basically fits. We do a good job there. So indeed it works that we can actually shine light against this molecule and see the bonds. We're only looking at about 50 molecules in this gap here, all at the same time, but you can see they're all identical. Except at some point in time, something happens. So we've now studied this for a few years. People have studied it for 30 years and not really understood it. And now I think it's clear that we understand it. What happens at this moment here is that a single gold atom is pulled out from that facet by about half its diameter, as far as we can tell. And the way, if I try and solve electromagnetism now, I have a problem because I'm trying to do it around a single atom, and I shouldn't be able to use classical mechanics for that. So we've used these very tiny 1 nanometer chunks with the full quantum theory to show that, okay, the hand waving is not so bad. When I solve it, this is actually acting as a lightning rod on the single atom scale. So it concentrates a field. A lightning rod will actually concentrate any electrical field into it because it's very sharp. And this is now working at optical frequencies on the single atom scale, and it concentrates the light still further, and it concentrates it near this bond. So what we see here is an individual bond of an individual molecule next to that gold atom. And we can watch it for minutes at a time. You can see it wobbles around. So although we're told that this bond here has always the same energy, it's not true. And it's because this gold atom is stealing some electrons from that bond. We think it's stealing about 1/6 of an electron, so quite a big, strong bond here. And so it makes that bond weaker, which is why this is downshifted in energy. And we can make some sort of DFT calculation which looks nicely in comparison to the data, but then again we're still making this incredible assumption that we can treat our gold atom as a classical object, and that the DFT is not done with all the gold atoms around and all the electrons, so there's a lot going on here. So this is now a new field that's called molecular optomechanics. It's essentially something vibrating coupled very strongly to molecules and also to this optical cavity. And trying to do all the quantum of this together is just beyond what people are able to do. So again, I hope I'm trying to convince you that this classical quantum boundary. Yeah, so that's the calculations we've done so far on a nanometer scale object. And if you look at the optical field in the full time-dependent DFT, it sort of gets close to what we see in the classical calculation. But we don't understand even why that works. There are all sorts of other things that we're seeing as well. So for instance, in recent work, so I'm showing the same sort of Raman spectrum here. This is the sort of event I showed you before where a new line appears, which is coming about because one of the gold atoms has moved and it's changing one of the bonds here. We can measure it. But sometimes we see something completely different. We see something sort of glow very briefly. And it's only because we're looking at very small volumes of space we're able to sort of see these things going on. This is a sort of looking at materials on the nanoscale, and it beats any electron microscopy that we can do because it's so fast. So trying to understand that, we now have a theory, which is that we think this comes from the fact that you can have defects in the gold. And the defects, well, actually, we think it's probably a twin boundary, so it doesn't look quite like this. But essentially, the gold atoms maybe have a different stacking, ABC, ABC, and here CBA, CBA here. So slightly different stacking. So in between, there's some sort of grain boundary. And we think what happens is the properties of the metal are different to that grain boundary. And in particular, the plasma frequency. So the plasma frequency is essentially how we think about electrons sloshing around inside the gold. And we normally learn it in undergraduate. It just depends on the density of electrons and their mass. So it's normally considered a fundamental for any particular material, for metal, say. But here, what it looks like to us is that this plasma frequency of this small region here, which is a couple of nanometers across, is actually much, much less than the plasma frequency of the bulk metal. But that's not a concept we have in plasma frequencies. Plasma frequencies are not supposed to be local. And it's not even clear what it means to have a local plasma frequency. So again, we find this sort of problem of when we're looking with light at very small regions of space, we find ourselves challenged by lots of these different questions. So what I hope I've done in my 25 minutes is give you an idea of a scale of problems when you're trying to connect light with matter. And the reason that you go to the nanoscale here is when you go below the wavelength scale of light, you can manipulate that light-matter interaction really strongly, which is also what we do at larger frequency scales in our mobile phones for antennas and a whole variety of other things as well. I'm most interested in trying to do it in the sort of visible frequency scale. How do we make things work at that scale? So how do we make materials? These we're trying to, for instance, make building coatings which change color. So when it's a hot day, it's silver, so it reflects the heat load from the building, but when it's cold, it goes black, so it absorbs it. And already we have nothing like this. We don't have wallpapers that change color. So Pilkington make this glass, very expensive glass, and it's too expensive even for them to actually put it in showcase demonstrators. It's just ferocious. So that's why we're trying to use these ideas to make more functionality, but at the same time, we come very quickly against fundamental problems. Often we don't understand things like disorder. We don't understand how self-assembly works, so interactions on this nanoscale. Even defining what electromagnetic simulations might look like on this scale are very tough, because now my light can be even confined on this 1 nanometer scale, and then it's not even clear how I set up a problem. So this classical quantum boundary, I think, is very interesting. Now we can ask the question, what's the forces coming from this confinement? So when I have a gradient of the optical field, like you can see here, that normally comes with with optical forces. So a dielectric wants to be in a high field region. It seeks high field, so it should move towards it. So this should completely deform molecules, and we don't really understand what's going on or what the scale of the forces are, because we can't use any of the normal formalisms for doing that. And then there are ideas about, what does a material actually mean on this length scale? Do we have to think in a sort of atomic terms, or it's not really atomic, it's not really a full medium, something in between is what we need as well. So I hope that's been stimulating and given some problems. Great.
So yeah, you mentioned that it's very complicated to understand.
Mm-hmm.
But in terms of nanoassembly, are we at a stage wherein we can deterministically manufacture something and it will be blue in color or red in color before a process?
So the good thing about an opal is all it requires is order of spheres. And that one turns out to be completely doable. So spheres we can do. But if I want to make anything more complicated than that, we can't really do. I mean, the people are trying to use, say, selective DNA interactions to be able to do that, and that also turns out to be incredibly difficult. The main reason is that either you have to have something, a force on that scale, which is driving you towards a particular state, which is a metastable state. It's not say, the thermodynamic state. You drive it to that state and you set it. Or you have to have a thermodynamic state, which is the one you want, but then it's very hard for the system to find it. So annealing becomes very important, and how you anneal. And the hierarchy of interactions is what people have learned is very important as well. But it's certainly, it's a massive problem. And yet, we know it's doable, because our bodies work by protein machinery, which is exquisitely assembled and works fantastically well.
This is my next question, actually. So are nanoparticles there in nature? So can we see this phenomenon anywhere? Have I missed something?
So in nature, you'll see butterfly wings, which use the same idea of structural color. They don't use spheres. They use a more complicated topology, which has emerged from times. They use a phase segregation to actually make it happen. It's a block copolymer, if you like, two immiscible sorts of polymer materials which phase separate, and it's very carefully controlled, probably by some very exquisite protein machinery, the scaffolding that people don't really understand at the moment. So we can't imitate that at the moment.
So at the beginning of your talk, you mentioned this shear-induced crystallization. So do you get HCP or FCC or any old stacking sequence?
Yeah, that's a really good question. So it was actually very, very hard to answer for a long time. We had to painstakingly slice samples and start mapping. And so the answer seems to be it's most closely related to random stacking, but not completely. There are some next neighbor interactions. We would really like to understand it because we would like to be able to control that as well. So for instance, with the shearing, so actually it's beautiful. Now we made this industrial process where we shear it around a roller. And it's because it's a different path, the outside goes a longer path, so you just get a very precise shear, and then you can bring it back again. But of course you can tilt your rollers, so you can do it first in one direction and then at 60 degrees to it. And then, or you could do it, you could do a whole variety of things, which should probably make those, control the interactions. But we don't know what we should make yet. So that's a really good interaction.
So in your pico cavity thing, is there a connection to SIRS? I mean, can you get the effect also with...
Yeah, so this is all working as surface-enhanced Raman scattering. So the fact that we get very strong fields inside these gaps it amplifies enormously the Raman scattering, and that's why we can see 50 molecules or even down to one molecule or one bond. So as we learn how to localize light tighter and tighter, we actually realize you can look at one bond in real time in ambient conditions and do chemistry.
So you could use silver as well?
You could use
silver.
Silver works just well, but of course silver oxidizes. So we mainly stick to gold because it's, we've got enough problems. So one of the interesting things is that this gold atom that gets pulled down, it really literally gets pulled down. It's the light that forces this gold atom down. We can then reduce the light level and it'll be stable there, and then when we increase the light we can push it back in again. So that's why we know the forces exist, we know the sort of energy scales, but we don't know how it happens. So we have an idea of gold, it's a solid at room temperature, but that's the wrong model. It's solid in the bulk, but the surface atoms are more like soup. And they can move around easily, and particularly when you have light on them, they can really move around easily.
What is it? Thiocyanobiphenols or whatever it was.
Exactly.
That will wobble as well. Bring it
I agree.
Closer or further away.
Yeah, it's true. But in fact, so it comes back to the intuition again as well. We often like to think as metals as solid, you make swords out of it, and molecules as floppy things. It's completely the wrong intuition at the nanoscale. Covalent bonds are extremely strong, rigid objects, directional, and the ductile gold atoms are sort of little frothy things that float around, that they don't produce much force.
Yeah, but the connector to the gold at the bottom should be flexible, I believe. I mean,
no, but, so of course you're saying something right. Yes. So indeed it's true, When this gold atom moves out here, what you can see are changes throughout the rest of the molecule, and we can track that. I mean, you actually sort of see it here directly. So these changes are in the rings. There's a whole lot of changes that you can't just see that are in there as well. And in fact, what we're doing at the moment is we're trying to take all this data and reconstruct precisely the position of all the bonds and the gold atom there. And we think we can get that gold atom to about a picometer at the moment. And for instance, there's a twist around those rings there. They'll twist like that, and we think we get that to about 0.1 degrees. So that reconstruction is depending on DFT. Now, it somehow happens that this system here, with this very simple molecule, is amenable to our taking it apart in this way. Most systems that we look at are just ferociously complicated. We see lines going all over the place here. So we do it with DNA, for instance. We do it with lipid systems, all sorts of interesting systems where we can do photochemistry, photocatalysis. And so this is, if you like, our prototype system, because it's very robust and we see these only occasionally. We can sort of try and tease apart what's going on. But it teaches us that our current theories don't really, they're not really right. Okay, thank you.